Hey, AP Statistics. We are going to do the first couple of pages of chapter 11, 12 notes. And so our textbook is a little bit old, and so chapter 11 and 12 are now combined. So that's how we're going to do this chapter. So chapter 11 and 12 are on significance tests. Okay, so if you've heard of that, awesome. If not, I'm going to tell you all about it. So a significance test is a formal procedure for comparing observed data with hypotheses whose truth we want to assess. Okay, so basically there's going to be a claim, a company claims something, and we want to show that we have sample data that shows that their claim is incorrect. Okay, so the hypothesis statement is a statement about a population parameter. Such as the population mean mu or the population proportion p. The results of a test are expressed in terms of a probability that measures how well the data and the hypotheses agree. Okay, we've kind of been talking about not just finding the probability, but then we're also going to draw conclusions, and that's where this chapter kind of starts to have us draw conclusions about what we see. Okay, so there are 6 main steps to a hypothesis test. We're going to kind of go through an example and walk through them. So a null hypothesis is the statement being tested in a significance test. The significance test is designed to assess the strength of evidence against the null hypothesis. Okay, so this is a big thing that it's a great multiple choice question. The significance test is designed to assess the strength of evidence against the null. So our sample data is trying to show that the null is not correct, okay, that it's changed. So we're not supporting the null, we are trying to find evidence against it. And the null hypothesis is testing that nothing has changed, like the claim is still true. It's abbreviated as H sub 0. Okay. The alternative hypothesis is the claim about the population that we are trying to find evidence for. Okay, it suggests something has changed and that original claim is not true anymore. And this is abbreviated H sub A. And I do have a lot of students call them the ho and the ha, which is totally fine if that's what you want to call them. But the null and alternative is what they're called. Some notes about hypotheses. Hypotheses always refer to some population. So these will always be in terms of either mu or p. You always want to state the null and alternative in terms of the population parameter. Okay, so in terms of mu or p. Writing our hypotheses in terms of a sample values like x bar on the AP exam will be severely punished. Okay, so note to self, I will punish you too if you write that on a quiz or a test. Okay, so it's not good. It's common to use some sort of equal sign in the null hypothesis. So whether it's an equal to, greater than or equal to, less than or equal to, you need to have some sort of equal in the null hypotheses. And then there's usually no equal in the alternative. So it's a not equal to, it's strictly less than, or strictly greater than. Okay. A one-sided test involves the alternative hypothesis testing in one direction. So strictly we think it's just less than or greater than. A two-sided test involves the alternative hypothesis testing in both directions. So it just has to be far away in either direction. So that's a not equal to test. So we're going to walk through this example and kind of go through the pieces of our hypothesis test. So several cities have begun to monitor paramedic response times. In one such city, the mean response time to all accidents involving life-threatening injuries last year was a mean of 6.7 minutes and a standard deviation of 2 minutes. The city manager shares this information and encourages them to do better next year. At the end of the following year, the city manager selects a simple random sample of 400 calls involving life-threatening injuries and finds the mean response time was 6.48 minutes. Do these data provide good evidence that the response times have decreased since last year? All right, so in problems like this, we're going to have a lot of information, okay? It's going to be very similar to last chapter where we do the analyses for means, and then we're going to switch and do it for proportions, okay? So we kind of want to highlight some things that we have in here. Okay, so, and I have the symbols on here to kind of help us as we get started too, but we have the population mean is 6.7 minutes and a standard deviation of 2 minutes, okay? And so this is different than last chapter. Last chapter, we didn't have the population mean. We were trying to estimate it with a confidence interval. And now we have both the population mean and the population standard deviation, okay? And then as we keep going, we can see that there's a couple other things we want to have. We have a random sample of 400 calls. Okay, so that's good. And then this sample provides a mean response time of 6.48 minutes. So that that mean is based off that sample of 400. So that's our X bar. Okay. Okay, so now we want to write the null and alternative hypotheses. So the null we write H sub 0. This is going to be a mean problem, so we know we're talking about mu. The null hypothesis is nothing has changed, so the initial mean is still the same. So in this case, we would say that the mean, mu, is still equal to 6.7 minutes. Again, the null is that nothing has changed. The alternative hypothesis usually comes up in the last question. It says, do these data provide good evidence that the response, oops, sorry, that is not what I want. There we go. That the response times have decreased since last year. So we want to show that the mean has decreased, okay? So our alternative hypothesis, the H sub A, is that mu has decreased from 6.7 minutes. Okay, one thing to point out is that notice that mu of 6.7 is in both the null and alternative. I am not saying that the new mean is our sample mean. I don't have to say that it equals 6.48. I am just saying that I think it's less than the number that they previously reported. Okay, so those should always match. The numbers that's in the null should be the same in the alternative. Okay, so conditions for a significance test. You're going to recognize these because they're pretty much the same as confidence intervals. Okay, so we've got that down. So we've got a simple random sample. We need that it's approximately normal. So for a mean problem, there's a couple ways we can get it. Well, the population is stated to be normal, or we have a large sample size, greater than 30 by the central limit theorem, or we have raw data that we need to check. Okay. For proportions, remember the sentence if, we'll talk about proportions later, but if we know P, we're going to use P. These problems, we're going to know the population parameter, so we're going to be using P in our checks. Okay, so the conditions we should be pretty good with since those are exactly the same as what we saw last chapter. Okay, so you're going to start to see that as the chapters go on that the data or the stuff that we're doing, it just starts to be very similar from the previous chapter. Okay, the applications are the same. Okay, so test statistic, that's the next part. Okay, so the first was the null and alternative. The second part was check your conditions. The third part is the test statistic. Okay, the test is based on a statistic that compares the value of the parameter as stated in the null hypotheses with an estimate of the parameter from the sample data. Okay, can you think of something that we have already that we've done where we're able to compare a statistic, so like our x bar compared to our mu, and tell how far away that is? What's the likelihood of having a sample mean that far away from our population mean? Yeah, so if you can tell where we're going, you can see the test statistic. This is just finding a z-score, really all it is. Okay, so again, this is a piece that we already know how to do. Values of the estimate far away from the parameter value in the direction specified by the alternative hypothesis give evidence against the null. Okay, again, we're trying to find evidence against the null. To assess how far the estimate is from the parameter, we're going to standardize the estimate, and generally in this form. Okay, so the test statistic was going to be a z, our estimate minus the hypothesized value, and divide by the standard deviation. Okay, so from the example that we're working on, we have the population standard deviation, so it's going to be a z. Our x bar was 6.48 minus the population mean of 6.7. But did you notice, we didn't really go through all the checks, but did you notice that we're taking a simple random sample? Okay, once we start taking a sample, we have to divide our standard deviation by the square root of n. Okay, in the other problems, we just kind of done this as like a side note. We already found the mean and standard deviation. Here, we're just going to do it all at the same time. So we're going to do our standard deviation of 2, divide by square root of 400. Okay, so again, this is like the z test statistic, and then we're also combining what we know about standard deviation from our sampling distributions. Okay, so grab your calculator and go ahead and calculate that. You can do this all in one step, and that's what I would recommend. Just make sure you use parentheses. Okay, so here you should get negative 2.20. Okay, if you have calculator issues, go ahead and pause this and talk with your neighbor. Okay, so we got the test statistic, we got the standardized value. The p-value is basically the probability. So if we have a z test statistic, can we guess what the p-value is going to be? How likely is that? How do we do that? We do normal CDF. Okay, so again, these are all pieces that we know. We're just kind of putting them together. So the p-value is a quantitative measure. It's a probability of just how unlikely a given finding is, assuming that the null is true. Highlight this. We are going to come back to this in the future. P-value. We're assuming that the null is true. Okay. The probability is computed assuming that the null is true, that the observed outcome would take a value as extreme or more extreme than the actually observed value is called a p-value of the test. The smaller the p-value, the stronger the evidence against the null hypothesis, which again, that's what we're trying to find evidence for, against the null. So that's what we want. Small p-values provide evidence against the null because they say that the observed result is unlikely to occur when the null is true. So therefore, we have evidence that the null has changed. Large p-values give evidence for the null. P-values are exact if the population distribution is normal and are approximately correct for large n in other cases. Okay, so this goes back to basically our normal assumption. If the population distribution is normal, then our sampling distribution will also be exactly normal. So we get exact values. If we've had to show that it's approximately normal, by checking raw data or using the CLT, then we just get that it's approximately correct when we have a large n. Okay, so for the z-score above, we're going to find the p-value. So we're going to draw our little curve, normal curve. So we're centered at 6.7, and we wanted our value that we have is 6.48. And this shading is going to match our alternative hypothesis. Okay, our alternative hypothesis was that mu was less than 6.7. So notice that we're shading this in the same direction. We're going smaller than. Okay. So we're saying what's the probability our x bar is less than 6.48. It's going to equal normal CDF, negative infinity, to our z-score that we found for it, which is negative 2.20. Okay, so go ahead and calculate that. Okay, so this you're going to get 0.014. So the probability that we get a value that far away, it's only 1.4% chance that we should be able to get something that far away if 6.7 is true. Okay, so far we've pretty much done almost all of these pieces. Now we're going to come to something that's a little bit newer, and this is where we have our our cutoff value for what we consider it could have plausibly happened versus it's very unlikely to happen. Okay, and so this is called whether it's statistically significant. Okay, so we're going to compare the p-value, so this answer that we just found up here, to a fixed value that we regard as decisive. This value has to be decided in advance. So you have to decide how much evidence against the null is needed. The decisive value of P is called the significance level. And is denoted by alpha. So this is like a Greek symbol alpha. Okay. If we choose alpha of 0.05, we're requiring that the data give evidence against the null so strong that it would happen no more than 5% of the time when the null is true. Okay. If we choose an alpha of 0.01, we're insisting stronger evidence against the null, evidence so strong that it would appear only 1% of the time when the null is true. Okay. These are pretty common alpha levels to use. They kind of correspond with like 95% confidence and 99% confident. So those are going to be the ones that we're going to see most often. Okay, so if the p-value is as small or smaller than alpha, then we reject the null, which means the data is called statistically significant. So when we reject, when we're rejecting, that is called statistically significant. So you'll have questions that say, is it statistically significant? And that's just asking, would you reject this decision? Sorry. Okay, so before you turn the page, at the bottom of your page, I want you to write it. This is what I want you to always check. P-value less than or equal to alpha, then we reject the null. And I want you to put a big box around this and highlight it. Okay, that is what our decision is going to be based off of every single time. Visually, what's happening is that if we say we have like some small value over here, or the other side, doesn't matter, but we're having this cutoff value of alpha, where alpha, like to this part, would be like 5%. So if we're saying our value is within that 5% boundary, then most likely we shouldn't have been able to get something that's that far away. So we're going to reject. Okay, so alpha is this like cutoff value for where we think our likelihood changes from it's not that likely to occur versus it could have happened by chance. Okay, so go ahead and flip the page. If the p-value is greater than alpha, then we say we fail to reject the null. And it's called that it's not statistically significant. Okay, so we were close enough that our sample value could have happened by chance, and it's not really showing evidence against the null. What I want you to put on the side or somewhere is that we don't agree with the null. We don't accept the null. Any of those things, this is not what we're doing. We are saying that we failed to reject it. We can't reject it. That's all we're saying. And all we're saying is that if we took a different sample, we could come to a different conclusion. So with this sample, we can't reject it. Okay, that's all that we're saying here. Common significance levels include 10%, 5%, and 1%. So you'll see alpha levels of 0.1, 0.05, 0.01. Okay. And there's no sharp border between statistically significant and not significant, only increasingly strong evidence as the p-value decreases. Okay, so for our problem that we're doing, we want to compare p-value, is it less than or equal to alpha, and then we're going to reject the null. So our p-value was 0.014. We were going to use an alpha of 0.05. Okay, so 0.014, is that less than 0.05? Sometimes people have problems with the comparing small decimals like this. So in your head, you can always multiply it by 100. So you're comparing is 1.4 less than 5. Okay, it's the same thing. So yes. Okay, so then we're going to reject the null. That's our decision. We're rejecting the null. And then we just have to write basically a sentence interpreting our results in the context of the problem. And there's a few pieces that the AP exam is going to look for within your writing. And so we just want to make sure we include those. Okay, your conclusion should have a clear connection to your calculations and should be stated in the context of the problem. This bullet is straight from the grading scales of the AP exam. This is what they're going to look for. You only have two options. You're either going to reject the null or you're going to fail to reject. You don't agree, you don't accept, you don't do anything. You either are rejecting or you can't reject. Okay? It does not mean that you're agreeing with the null. It means that the sample does not provide evidence against the null. That's all this is saying. Reject the null if our sample result is too unlikely to have occurred by chance, assuming that the null is true. And we're going to fail to reject if our sample result could have plausibly happened by chance, assuming that the null is true. Okay, so in both of these cases, we're assuming the null is true. We'll come back to this in the future, but I just want you to see those key things. Your conclusion should include the significance level alpha and include linkage between the p-value obtained and the conclusion. Okay, something of the form, the p-value is so small that we have strong evidence against the null. This, again, comes straight from the grading of the AP exam. So I'm going to show you how to write your sentence correctly. And last note, alpha should be chosen before the data is collected. You can't look at your result and then determine what alpha level you need. You have to have decided that beforehand. Okay, and that is true for any type of thing that you've had to test and show that it works significantly better. So any type of pharmaceutical drug like Tylenol, Advil, whatever it is, if they're trying to show that Tylenol is a fever reducer, they have had to choose their alpha level before they did their study to show that, yes, Tylenol does significantly reduce a fever compared to a placebo pill. So this is regulated and part of a court hearing or anything like that. You would have to have chosen your alpha level before you see the results. Okay. Typically in court cases and things like that, the standard level for alpha is 0.05. Your book is silly and doesn't really state the alpha level very often, so you can always just assume alpha is 0.05. Same with on the AP exam. If for some reason they didn't give you an alpha level, you can just state, I'm going to use alpha 0.05 and then base your conclusion off that. Okay. Okay, so what we're going to write as our conclusion here is since our p-value is less than or equal to alpha, which was 0.05, we reject the null. So what we're going to say is there is sufficient evidence to suggest that the mean response time to all life-threatening accidents is less than 6.7 minutes. Okay, so that if we're rejecting, we rejected the null. So that means like in this situation, we said it's basically statistically significant. If you reject, it's considered statistically significant. All right, thanks for tuning in. I'll talk to you guys later.